In this section, we'll discuss design strategies and materials that are used to keep the body cool in warm environments. In warm environments, our major goals are to get rid of body heat effectively and to protect the body from environmental heat. To do that, we're going to do everything we can to promote thermal transfer from the body to the environment and to inhibit thermal transfer from the environment to the body. First, let's talk about getting rid of body heat. Because it's often the case that the environment is the same temperature or hotter than the skin, conduction isn't a really useful mechanism for transferring body heat to the environment. If the environment is warmer than the skin, thermally conductive materials will transmit heat to the body instead of away from the body. Similarly, radiation is more likely to come from the warmer environment toward the body. So thermal transfer from the body is most effective when we can circulate air and promote the evaporation of sweat. Phase change is one of the most effective methods of cooling, and evaporation of moisture can be a great way to achieve phase change in the right conditions. If you've ever lived in a dry, hot climate, you may have seen indoor cooling devices called swamp coolers that work by blowing air over a wet surface. The evaporation of moisture from that surface cools the air as it passes over, and this can work as well as an air conditioner in the right conditions. So let's talk about sweat. As we discussed in the body thermoregulatory systems section, the effectiveness of sweating depends on some environmental factors that are outside of our control, like the relative humidity of the air around the body. But assuming that there's somewhere for the sweat to evaporate to, clothing can help move that sweat around in useful ways. Generally speaking, fibers and fabrics do one of four things. They can absorb moisture into the fiber, adsorb or hold moisture onto the outside of the fiber, wick moisture along the length of the fiber, or repel moisture altogether. Which approach is best depends on the nature of the problem that you're solving. There's two goals involved. One is, of course, to help promote thermal transport by evaporating sweat if possible. But the second is to keep the user comfortable by removing moisture from the surface of the skin. Wet skin in general is not very comfortable. Fibers that trap moisture by absorption or adsorption usually inhibit evaporation. But in situations where the sweat has nowhere to evaporate to, like in a hazmat suit or a fire entry suit, sometimes absorbing it off the skin and trapping it somewhere else is a better option. For more extreme absorption, superabsorbent materials are required. Superabsorbents are materials that can hold many times their volume in liquid. Most are hygroscopic hydrogels, polymers that grab moisture and resist releasing it. These materials are in most disposable absorbent products like diapers and feminine care products. You may have also seen them as the clear jelly beads in the base of a floral arrangement. Superabsorbent powders are also used to make fake snow since they fluff up when they're saturated. Superabsorbents are extremely effective at pulling moisture away from the body, but a key drawback is the length of time it takes for them to dry out. It can be days or maybe weeks, depending on how much moisture was absorbed. For that reason, they're more commonly used in disposable products. To return to our basic mechanisms, fibers that repel moisture would make evaporation easier from the surface of the fiber since they have so little attraction to the moisture. But they don't do any transport of moisture, and sometimes that means putting the sweat back onto the skin. Wicking does a better job of moving moisture away from the skin, so we'll discuss that a little further. Wicking operates by capillary action, which pulls liquid along a channel by surface tension. Wicking fibers are usually formed with grooves along their length, which form these capillary channels. The basic principle behind wicking is that liquid moisture can be picked up from the body and transported along the length of the fiber, which winds in and out of a knit or a woven fabric. And the process of transporting through these small channels spreads the liquid out, and eventually the liquid will reach the outside of the garment where it can more easily be evaporated. There are a few things that people often misunderstand about wicking. First, remember that wicking only works for liquid sweat. It doesn't work for vapor or humidity that's coming off the body. Second, the wicking fiber must be in direct contact with the liquid moisture. Wearing a wicking garment over an absorbent garment like a cotton t-shirt would defeat the purpose. Third, the garment system must be layered in a way that the outside of the wicking garment is exposed to air, or preferably to moving air. Otherwise, the liquid will have nowhere to evaporate to. So if you wore a wicking garment trapped underneath an impermeable garment, it wouldn't be very effective. Finally, as with all moisture transport, the environment must be able to accept that evaporation. If it's too humid, the liquid won't have anywhere to evaporate to. So given these factors, wicking is obviously not the only solution to moisture management in garments. For example, if your user is likely to be sweating very lightly with very little liquid sweat, a loose-fitting absorbent garment that allows airflow and removes humidity and vapor from the skin might be a better solution. So wicking works for liquid, but we might also need to manage vapor. Absorption is certainly one method that can be very effective, but I want to highlight another important fabric technology that manages the competing goals of keeping environmental moisture like rain off the body while allowing body vapor to escape. Waterproof breathable fabrics manage this through a few different mechanisms, but the original Gore-Tex technology patented by W.L. Gore uses a microporous PTFE or polytetrafluoroethylene film. PTFE is Teflon, the same stuff that's on your nonstick pans. Gore discovered that if you stretch out a Teflon film, it starts to separate into little islands surrounded by fibrils, as you can see here. Those tiny gaps of the fibrils are big enough to let water vapor molecules pass through, but not big enough to let liquid water droplets pass through. So it's used in garments that need to be water resistant, like raincoats, to make them more breathable by letting body vapor escape through them. There are a few important things to remember about PTFE though. It's relatively fragile, so it needs to be protected with a laminated scrim or a textile on both sides, and it will eventually break down in areas that flex a lot. It's susceptible to clogging when dirt gets into the pores of the film and blocks that vapor transport. Lastly, it doesn't work for liquid sweat, which is also too big to pass through the holes. So once the wearer really starts sweating a lot, it's going to act more like a plastic bag than like a breathable textile. There are also other approaches to waterproof breathable fabrics that use combinations of hydrophobic and hydrophilic materials to pull more moisture through a layered textile. Within a garment system, sometimes we're interested in keeping the wearer cool while also providing some other layer of protection, which sometimes directly opposes the goal of circulating air and promoting evaporation of sweat. For example, we might want to protect an athlete from abrasion or impact, which requires covering the body, but also keep her cool at the same time. Spacer fabrics can be useful for this purpose. We also discussed spacers in the keeping warm section, and here we're talking about the same materials. The only difference is whether or not you're allowing airflow through them. A spacer just creates an airspace, like this ladder knit. If air is not allowed to enter or leave the spacer, it's a really good insulator because of all the trapped air. But if you allow or even promote the airflow, it becomes a very good ventilator. Spacers can be made in many different materials and structures. You'll often see them in the straps and backs of backpacks to lift the pack off the skin and allow the air to move beneath it. For even better ventilation, supplemental airflow like fans or pumps can be used to move air through the wearable system. Fans are lower power and lighter weight than other forms of supplemental cooling, and they're common in garments with a lot of airspace, like theme park character costumes. Another important consideration for airflow in a garment system is the ingress and egress of the air, how air gets in and how air gets out of the garment. Vents can be designed into a garment to allow air to enter and leave, and they're attractive because they can be opened and closed by the user to kind of customize the amount of airflow that's going on. For example, this jacket is designed for cyclists, and it has a vent on the dorsal shoulder that catches air when the user is in a cycling position. Another vent on the lower back allows that air to exit the garment. There's two common mistakes that make vented garments like this less functional. First, designers often forget to give the air somewhere to escape. If a garment only has an inlet and no outlet, it might still help ventilate, but it won't be as effective because the airflow is limited. Second, designers often don't take into account the position of the vent opening. If the vent doesn't stay open, then the vent's not very useful. The techniques that we discussed in the mobility unit for working with on-body forces can help with designing vents that work with the tensions on a garment during movement instead of against them, so that body movements will open the vent instead of holding it closed. Unlike in cold environments, to cool the body, you'd want to take advantage of the two garment level effects that we discussed preventing in the keeping warm section. The chimney effect can be used to let hot air escape out the top of a garment and then pull cooler air in behind it. And the bellows effect can be used by designing the vents and garment shapes to work with body movements to pump air around the body. So let's come back to the question of phase change and how it's used to remove heat from the body. Sweat has been the material that we've been focusing most on to transport thermal energy through phase change, but cooling can be achieved with phase change of any material. In fact, that's how your refrigerator and air conditioner work, by compressing a gas until it becomes liquid, then releasing the pressure to allow it to change back to gas. That transition from liquid to gas pulls thermal energy from the environment and cools it down. Wearing a compressor is not necessarily the most appropriate or comfortable solution, which is one reason why air-conditioned clothing doesn't really exist yet. In space, the liquid cooling garment that astronauts wear uses the vacuum of space to allow liquid to become gas very quickly, which cools water inside the suit as it runs over a plate. That cooler water is circulated around the body through tubes in the base layer garment. Unfortunately, on Earth, we don't have that handy vacuum to help with the phase change. But liquid cool garments that are attached to a portable compressor do exist for some extreme environments. A less intense version of phase change temperature control is provided by so-called phase change materials, or PCMs, which are materials that melt and solidify at specific temperatures. The idea behind them is that these materials will be solid at some temperature that's close to the temperature of the body, and they'll melt when body temperature increases, taking heat away as they do. As body temperature drops, the material would re-solidify and deliver that heat back to the body. In practice, it's difficult to encapsulate enough material to do any sort of dramatic temperature control. The most extreme version of this approach is big packs of phase change material that work kind of like ice packs. Phase change textiles usually use microencapsulated phase change materials, so the amount of material that can actually be embedded in the textile is pretty small. These materials are better for regulating a really small change in temperature, not for extreme changes. So now let's talk about keeping environmental heat away from the body. Many of the techniques we discussed in the keeping warm section also apply here. Just like an insulated food or drink container can keep a warm thing warm just as well as it can keep a cold thing cold, insulation just keeps temperatures from changing across a barrier. It might seem odd to want to keep body heat in when you're in a hot environment, but in a very hot environment, sometimes that's the best approach. For example, firefighter gear uses insulation that traps air to keep extreme temperatures away from the body, just like an oven mitt does. Yes, at the same time, this also keeps the firefighter's body heat in, but it's better to be slightly overheated than to be exposed to the extreme temperature. The principles and methods of measuring insulation were discussed in the keeping warm section, so I won't spend much time on them here, but they would also apply for keeping cool. In warm or hot environments, protecting the body from the radiant heat of the sun is important. Garment surfaces should serve to absorb, or even better, to reflect radiant heat away from the body. The same approaches to reflection that we discussed in the keeping warm section also apply here. For example, in space where there's no atmosphere to filter radiation, astronauts are exposed to a lot more radiant energy than we are here on Earth. The current spacesuit uses 7 layers of aluminized mylar to reflect this energy away from the body. Finally, advanced fabric concepts often explore textile structures that can adapt to thermal conditions by opening or closing. Pine cones are an example in nature of a material that responds to temperature and moisture with a shape change. The biologic vented fabric that you see here, developed at the MIT Media Lab, is an example of a fabric-like structure that mimics this behavior, opening small vents in the surface in hot and humid conditions.